All right, so I got a new video. So today we'll play around with this DESeq package to try to do some differential gene expression. And since I'm kind of an idiot and we're kind of, I don't know if we're necessarily low on time, but we're also not doing great with time. So I'm just going to keep going until I finished everything that I've wanted to say. It may take 30 minutes, it may take an hour. Who knows? Uh, Hopefully, you've at least installed these packages from the installation script that I ran. If you have any problems with that, if you had any problems with that one, let me know. But I'm just going to start building stuff out and kind of explain what I'm doing and also a little bit of what's happening behind the scenes. I'm not going to lie, looking at all of this stuff made me feel so embarrassed about how little I know about statistics and math tricks. So DESeq is definitely written by statistician mathematicians, and honestly, in some ways, I have no idea what they're doing. Um, Anyways, moving on. So I need to load in my packages, libraries. So I need my DESeq2 package, and I need my text import as well. These are the first two things that I need. Let me see. Let me see. TXI import. Okay, so this text import, it's not inherently required by DESeq. What it's going to do, what this text import package does, is that it imports um, read counts from our RSIM files and generates a matrix from that. So uh, let's so if we're looking at let's look at this real quick. So this is a RSIM output file. This is from Andy's. But if we're looking at columns, so we have the gene IDs, transcript IDs, they're the same thing. Length, effective length, expected count, TPM, and FPKM. So this expected count is the third numeric column. And this expected count is effectively the read count. It's the number of reads that map to that gene to some degree. So it's this third column, 66, 0, 0, 2, 0, 0, blah, blah, blah. And so it's this weird property. It's not really weird. It's weird that RSIM gives decimal values to this expected read count. Not entirely sure why it gives us a decimal whenever whole read counts should be a whole number. And I can tell you for sure DESeq will complain if you give it a data matrix that just has decimals in it. It will throw an error. It will cause some complaints. This text import helps with that, but you could effectively do the same thing. Is extract the third column from every single one of these files and round. That's really all it's doing. That's all this text import is doing. Is it's going to grab the third column from all of these RSIM files that I'm going to give it and round either down or round up. That's all it's doing. That's something I can and have done by hand. But I also kind of want to make y'all do as much as you can without having to use some script I've made. So text import helps with this. And so whenever we're messing around with text import, whoops, I need that. I need that over here. Why? So whenever we're dealing with text import, all that we're going to do is just import we need a list of file names. So I don't know if you looked at the manual and the tutorial about importing file names. It's very wonky, and it's designed in a way that all you have to do is point to a directory and it will just go ahead and load up all of your files in that directory as needed. However, it's a pain to make that work. It's a little trickier than it really has to be. All it's asking you to do is to make this files variable that's a list of file names, right? And so it's all of these file names that have these that have it's the RSIM output files, and all it is the file names in a list, or this vector. So that's one thing I need to do. However, whenever I make this list, it doesn't inherently come with the names. Whenever I directly import, say, my file list to text import, uh, it's not going to have column names. But I can go ahead and add column names to my file list by just throwing in a names file commands, and then naming this appropriately. So it should be named the file names. The file name should correspond to the file in the same order. So for example, I have MB liver, JB liver, GC liver, etc. And it corresponds exactly with the file names that have been called. Okay. And so once I have that, I'm ready to use my text import to read all these files and load them up. So I just call this data variable that's going to store all that. Tx import files. So files is just this list of file names, and I need to tell text import what kind of file type these are. And so it already has a definition that these are RSIM files. So I'm just going to save this real quick, as I don't want to save it there. I need to save it to all these files are in 435 Blast Express. So I'm going to call this DESeq .r. So I'm just going to have all my commands. Make sure that my working directory is set to the appropriate one and source this. Just what I've written down already. Make sure I don't have any problems. So it's loading up these packages. No major complaints yet. Still no major complaints. Invalid file argument. You lie to me. Why are you lying to me? Why? This is copied and pasted from a script that worked. Why is this not working now? Gotta love R. Files misspelling. Man, if you see something that I'm doing wrong, you can just tell me, or if you have any questions about what I'm doing, just tell me. Yeah, I just misspelled that file variable, so let me save this and run that again. And that seems to be better. All right, so now I have my text doc. And so this is a data structure that contains a lot of different stuff in it. So it does contain my count information. It also contains lengths of my sequences. So I can actually extract that from this text data. So text data $ counts. I'm going to head this. So it is kind of nice. I don't know if I mentioned this, but R does have the same command head. It works kind of the same. Gives the same import, same information. But right, so it's keeping count of our text of our count data, and so it just makes a new matrix. So this count matrix is just a new matrix that has all of the G names and all of those expression values, all those recount values found in all of our files, found from that list of files. But as I said, it also keeps track of length. And so these are all the gene links for all this stuff. And I think these gene links kind of go into play to make the expected read count. I think that's partially where we get the decimal from, but I'm not entirely sure. All right, but there is a stupid problem. There's a stupid problem that I had to find out how to fix. It's that some of these links of our genes, and it's just a property of our of the mouse CDS file. So if you recall, some of the shortest sequences I have in my mouse CDS file from this ensemble data, some of those sequences are only like 3 nucleotides long, and that actually will reduce down to an effective length of 0. And not RSIM, but DESeq will complain if I'm going to have sequences that are of length 0. Um, Most of these aren't going to have any expression values with them. So what I'm going to do, what I have to do, is that I have to change my lengths and change them so that any time that there's a 0, if I have a sequence of length of 0, I'm just going to change that to a length of 1. And so, as I said, nothing in R is intuitive, right? So this is a Googleable command. This is something I had to Google. Um, tx data length is equal to 0. And so what it's basically doing is highlighting. It's finding all of these. Um, it's finding all of my linked information that has a 0. It's finding that stuff, and then I'm going to change it. To change it to equal to 1. So anytime it sees a 0 for links, I'm just replacing that 0 with a 1. Again, R is pretty good at this kind of thing. That's not set equal to, that should be equal to. And so that, again, it's just something stupid that I have to do. Um, if you have a better library, or if I had filtered out all those transcripts that are less than 100 nucleotides or something else, something like that, I wouldn't have this problem. But because I have this effective length of 0, um, I have to change that. But again, I'm going to do some filtering here in a second. And so most of these genes that would have 0 length are going to have 0 expression. I'm going to get rid of those eventually later anyways. It's just whenever I import this into DESeq, it won't complain at me. All right, so what's next is I have to I have to define my columns. So I have all my liver, I have my row counts, I have my expression values from all my files, but I have to describe what those files actually kind of came from. And so I have to make a file. I have to make a separate file, and you will too. And this separate file isn't very fancy. It's just keeping track of my um, file names, or at least my names, my column names, and then a couple of attributes to them. So one, I have a species attribute, and I have a tissue attribute. I think I could reduce it even further to just tissue, but say I could develop a matrix that's full of multiple species and multiple tissues. I can at least define it that way. But recognize, like, whenever you're building this, this first row, these columns are tab delimited. It's just the first column is going to be the gene name, and it doesn't necessarily have to be defined. So I just have a tab species and then tab over for tissue, and everything else is tab defined. So don't use a space when you're building this file. Make sure everything is separated by a tab. It may be awkward for you to look at, but a computer will read this without any kind of problem. But again, all I'm doing is that I just have to define a little bit of property about this, about where the data came from. And it could be even further. So we could even add in, say, age of the animal, or if there was a diet before and after. So what we're doing, what the whole point of all of this is to identify genes that are highly expressed in liver that aren't expressed in kidney, and vice versa. Okay, so I picked these two tissues because I know there's going to be a lot of genes that are only expressed in liver and a lot of genes that are only expressed in kidney. But that's not necessarily that's no shit, right? Of course there are, right? typically when we do a differential sequence analysis, what we're testing is we're going to have a population of mice or something like that, and we're going to change its environment. We're more or less going to have a control group and then a treatment group, and we're going to compare expression of a single tissue in the control versus treatment. So, for example, if we had mice, we might build a control group that has a regular diet, but we might have a treatment group that has a really super fatty diet. Um, and so we may leave those mice on that kind of diet for a while, then sacrifice everything, pull out their livers and RNA-seq and compare what genes are highly expressed in a fatty diet population versus the regular diet population, or what genes are lowly expressed in the fatty diet population, things like that. So that's the whole point of this differential expression. It's not really to compare what genes are highly expressed in tissues, but change an organism's environment, or even do like a knock out a gene, make sure that protein can't be made in your treatment, and compare gene expression afterwards. See what genes are affected by the loss of that gene, right? So that's the whole point. But doing this liver versus kidney is just an easy way. I know there's going to be differential expression, and we can do this experiment. Now I don't have to go looking around on NCBI for these kind of treatment versus control groups and play around with it and spend a lot of time to find that maybe only 2 or 3 genes are remotely differentially expressed, and that itself isn't very fun. But we can at least walk through this tutorial using tissues. Moving on. So we have to import this file into R. Whoops. I need this over here again. Okay. So I need to import this file. And this isn't all that different. So I'm just going to call this columns. I hope I don't get myself confused. But this is just a read.table import. So read.table, you've seen this before. And so I think this table is specific, is called cold data.text. The header is true. So yes, the there are column names, and they're separated by a tab, right? So a typical a table import. Okay, so the next thing that we have to do is actually build a data set, build this matrix in a way using DESeq tools that will define how we're going to compare these values. So historically or traditionally, this variable is just called DDS. Any tutorial that I've ever seen is just we call this import file or import variable DDS. And so we're using uh, a specific tool that's DESeq data set from TX import. So a TX import was designed so people who don't have great Python skills or really any parsing skills, they can still use this package. Honestly, I've been wondering about it for a while, but I'm curious if you would just leave me a comment or a message, like what have you preferred this semester? Do you prefer working around with R a little bit more? Do you prefer the Bash environment, working around in Bash? Because it seems like I see y'all do the R assignments a little bit quicker, but I also recognize the R assignments are a little bit easier, and all I'm really asking you to do is replicate what I've done. But I am curious of what you've kind of preferred. What's easier to you is working in this R studio environment or Bash. But anyways, I digress. So DESeq from TX import, you can do, as I said, we can just pull out those columns, round down or round up, so they're whole numbers, and do a DESeq data set from matrix. Just read in a matrix table. I almost made y'all do that, but I kind of got lost, and I was unsure if text import, if it was doing something more than just rounding numbers up or down. Turns out, yeah, that's all it's doing. But I was worried it was doing more to account for gene length or something like that. But no, it seems to it's just pulling out the third column and rounding down or rounding up, whatever needs to be happening. But anyways, whenever we call this DEseq from matrix, it doesn't matter if it's TX import or matrix. We have to call the data that's holding it. So it's this TX import, TX data variable. This column, I need to rewrite the columns because that's the data table that's containing all of our information. And this variable, how we're controlling this experiment, what's really being, how are we defining our control and treatment groups? And so that's controlled by this tissue column, and having this tilde is just a traditional thing. It's required. Honestly, I have no idea what it's doing, but it is required. As I said, I'm going to get so we can look at this. I'm going to filter out first. So I don't want to have genes that are lowly expressed in this data set. Um, so I don't want to have genes with low expression. So I'm going to filter those out. I'm going to filter those out using this kind of, again, it's a wonky roundabout command. It probably makes no sense why I'm doing this. At least part of it will make any sense, but some of it's not. So I'm going to sum my rows. So I'm going to sum all the variables in my rows of my counts of DDS. And so counts DDS is going to actually return the count number. So if I try to head or look at this DDS variable, it's not exactly easy to look at. It's not intuitive to look at, but we can call this counts function that's going to look at our DDS file or DDS variable and return the counts as they should be. So I'm setting this variable or this vector called keep. And what I'm doing is I'm going to look through these columns or look through these rows and identify rows where the sum of the recount is greater than 10. And so I'm going to run all this stuff real quick. I'm going to update my script, reload stuff back in, and I should have my DDS. So DDS does take a little, or the DDS variable takes a little while to make. The keep makes no time whatsoever. But let's see if we can look at this keep. Let's see if I can head keep. No. Right, so all it is just a vector of true and false. It's saying, is the recount for the row sum higher than 10? True, if not, false. Right, it is this, I'm not filtering out now, I'm just finding rows that either pass or fail this benchmark. But then I have this other command where I'm going to call DDS again, but I'm going to have DDS matrix keep. And so it's basically going to say only keep the rows where this is true. So we're only going to keep true true rows. So we're going to filter out these lowly expressed genes because they're just hard to work with. Again, they could be artifacts, so we're just going to get rid of those anyways. All right. What else? Okay. So the first thing that I do want to hang on to, I need to find a couple of lines. Give me a second. I need to find these 3 lines. So I can keep out my my DDS numbers, my counts numbers. So this does take a little bit of explaining. So whenever we load stuff into DESeq or EdgeR or any kind of differential gene expression thing, we want to use the raw counts. But before we differential expression anything, we will normalize those recounts because our libraries are constructed a little bit differently. The sequencing depth of our libraries are different. how they're prepped. These are not necessarily standardized libraries. We just picked them off of the internet. So we're going to have to account for these variances by transforming our data, but it's going to be a little bit fancier in a way that I cannot explain. It's going to be fancier than an RPKM or a TPM transformation. Um, but DESeq will do that for us, right? Whenever we do the actual DESeq um, function, do the whole job itself, it will normalize all that stuff for us. But say we actually want to extract a normalized matrix and save that and hang on to that. Well, we can independently normalize our column data, or we can normalize our expression data separately from the actual DESeq experiment. So one of these is, again, these are just built in. These are just things that I know I have to do. I don't exactly know what they're doing. But either ways, we have to estimate size factor on that DDS. And I'm saving this as a new variable, DDS capital N. And then I'm also estimating a dispersion. Again, this makes me feel embarrassed that I can't explain size factors or dispersions in a statistical framework because I honestly have no idea. Um, but then I'm estimating this stuff, and then I'm going to measure the counts and normalize, have this normalized counts. And so I'll have this variable at the end of NDDS. So I'm just going to save all this stuff real quick and run it again. While that's running, I can save this matrix. Well, it will ultimately be a resulting transformed matrix that I may actually want to visualize later. I may want to make some graphs off of those numbers later. And so I will go ahead and save this count data. And so that should be as simple as a write.cvs in DDS and then my file name. So this will be live versus, I'm just going to say live versus kid norm.csv. Hopefully that will write without a problem. Okay. And so a CSV is just stands for comma separated. So it's the same thing. I'm going to open this up in Excel real quick so we can look at it. Let's Okay. So again, these are just, it's the same stuff. It's just instead of normalizing based off of a single library, it's taking the entire distribution of all of this recount information and then kind of transforming it and normalizing the data based off of the entire population of sequence data, right? But again, I just want to hang on to these numbers. I may use these numbers again, right? So I can, once I have these numbers in a table format, I can draw this stuff out. But I do just want you to recognize that this is comma separated. So all that means is that all of these columns are separated by a comma. And Excel can inherently read this. So any kind of CSV file or tab file, Excel can inherently read that for us and kind of make life easier for it. But this is what a CSV file actually looks like. Is every single column is separated by a comma. So let's see. So that's that. As I said, this is going to run long. Okay. I haven't even done the expression, differential expression yet. I'm going to hang on to that for a second. Okay. So the NDDS isn't going to be a part of the expression analysis. I'm just saving those values for later. Bring this back over. All right. And so the actual line, I'm gonna actually save this real quick. I'm gonna save that line real quick. All right, so now I am actually ready to do my differential gene expression. So basically, what's happening? Um, I'll just DES. I'll run it. It really doesn't take that long to run. It's just DESeq, and then the DDS file, right? So it's the non-transform data. Um, Again, DESeq, this function will just go ahead and transform everything for me and then run my experiments. So that really doesn't take all that long to run. But while that's going, what's effectively happening is um, it's going to look at the distribution of expression values for every single row, and it's going to look at the distribution of those values for kidney and liver. And it's going to do basically a statistics test on every single gene and say, um, is this distribution, is the sequence, is the expression distribution in liver the same as the expression distribution for this gene in kidney, right? So it's already done. This is already done, right? So that's the question at hand. And so in statistics, we have to have a population. We have to have variation. We can't just have two numbers and compare two numbers. Yay, one's bigger than the other. But we can't decide if that means anything. So to decide if it means anything, we at least have to have, even for differential sequence expression, even just a small population. Just 3 of each tissue is enough data to get away with. Um, but it's for every single gene, it's just going to run as statistics. And so, for example, let's say that for kidney, we have our expression values for among our 3 samples are 10, 12, and 15. But in our liver, those expression values may be 50, 60, and 70. Right? Those two things are very, very different. There's no overlap between whatsoever. So there's probably real differential expression of those genes. But for example, if we have liver saying 10, 15, and 20, and kidney is saying 15, 17, and 20, there's probably there's not a difference in those values. And so the statistics will kind of help us parse out if expression is the same in these tissues or expression is different, given what we supply to DDS. So we can summarize our results. Let me save that real quick. We can summarize our results by just calling results. So I'm going to make a variable called res. Again, this is more or less traditional based off of the tutorial. It's just a result. This result function is built in the DESeq, so DESDE. I'm calling the results of the differential expression analysis. And then I'm defining this alpha is equal to 0.05. So let's quickly look at whenever this gets done. Let's look at a result file, and I'll kind of tell you what that means. I will ultimately save this results variable as a CSV as well, because I can do some stuff with it too. So I need numbers. All right. Okay, so 2 of y'all like R more than anything else. Is it because it's replicating, or just the environment is kind of easier to work with? Like you don't have to worry too much about missing apostrophes or anything like that. Anyways, this is taking a little bit longer than I expected. This shouldn't have taken so long. Anyways, so what's happening is this results variable will contain the results of every statistic test for every single row. So I'm going to head results just to give sign. That's ugly. It's ugly as crap. Let's see if I can. I'm going to extend this over a little bit. Maybe I can get this all in one row. Okay, so for every row, um, we have the G name, or we at least have a transcript name. We have this base mean number, and this base mean number is taken into consideration all of our samples. What is the mean of that expression for that gene? Okay, and then there's a log fold change. Give me a second. I'll explain what that log fold change means in a minute. Um, what's most important, what's probably very important in these two rows, in each row, is this p-value, and more important is the adjusted p-value. So the p-value itself is it's given this stats test, given the distribution of our expression values. If p is greater than 0.05, then okay, there's probably a little bit of overlap, and expression is probably the same for that gene in these two tissues. But if that p-value is less than 0.05, it's saying there's a 5% chance or less that these genes, the expression of these genes and these tissues are different by chance alone. And 5% is just kind of the cutoff. So a 5% chance of being random is low enough to say it's probably not random. But when we're doing an individual statistics test on every single transcript, and in this gene set, I think there are more than 20,000 transcripts. So we're doing 20,000 individual statistics tests. And so if we have this p-value of 0.05 on any given test, that these results are the way they are by chance alone. And if we do that 20,000 times by chance, 5% of our expression analyses will be false positives. So we're going to have a p-value less than 0.05, but that doesn't really mean that they're differentially expressed. It's just an artifact of doing 20,000 different tests, and 5% of them by chance will show a difference. So what we have is an adjusted p-value. And so we account for doing multiple tests with an adjusted p-value. And so whenever I set this alpha to 0.05, it's saying, provide me, it's saying what's statistically relevant based off of an adjusted p-value of 0.05. Because if we look at this, that's not a good example. That's not a good example. So yeah, that's fine. So if we have this, let's look at our first row. If we have this 0.001, so there it's saying there's a 1 in 1,000 chance of this being different by chance alone. That's rare. That's probably real. But our adjusted p-value is higher. It's 0.005. It's 5 times higher. It's just by taking in consideration the distribution of our p-values and all this other nonsense. It's saying, okay, if we take into consideration all these other tests that we've done, our p-value is going, our adjusted p-value will be higher than the actual p-value, the raw p-value. So if we have a p-value of 0.05, the adjusted p-value may actually be like 0.07 or something like that. And so it's really saying, oh, these, if we take into consideration all these other tests, it's probably not differentially expressed. Whatever. It's accounting for these multiple tests. All right, and this log fold change, let me explain this log fold change real quick. So I'm going to bring back Excel because Excel is kind of easy to work with. So let's say I have a mean expression, let's say I have a lean expression in my kidney. So let's say my liver is, I have a mean expression of 10 and my kidney is a mean expression of 20. So my kidney is expressed in a way of 2x more than my liver. But I can ask, well, compared to the start, compared to my control, in this case, my liver is going to be my control. What was the fold change? How much did my expression increase, giving kidney, from liver to kidney? And so how we do this is doing a log2 transformation. So first we're going to we're going to divide these two numbers. So it's just going to be liver values divided by the kidney values, right? So that gives us a 0.05. But then we're going to log 2 fold change that. So we're going to log transform that, this value. So it's basically the expression of kidney divided by liver, and it's a log 2 fold, a log 2 transformation. And so now we get a -1. So what that means is that compared to liver, there has been a 1-fold increase of our gene in kidney. Okay, but let's say I change this value from, let's say I make this liver equal to 40. Well, now I'm going to have a positive number. And so it means that compared from the start, so our liver, from our, if we're calling liver our start, from compared to our starting point has 1-fold increase, or sorry, a 1-fold decrease. Our end has a 1-fold decrease compared to our start, or our liver. Right, but either way, we deal with these log transformations. We look for our fold change in gene expression. And so we'll see this log fold come out over and over again, because we're actually going to plot it out here in a second. But what I should point out is that if in our result, if we see a log fold change of greater than 0, it means that expression is going to be biased towards the liver. But if it's going to be less than 0, expression would be biased towards the kidney. That's kind of what's going to happen. So we should have some of these. Let me see. So for example, here, so there's a log fold change of ANOAPOH. There's been an 11-time increase. And so we have an 11x, or an 11-fold change difference that's biased towards the liver compared to the kidney. But over here we have this negative fold change by half that's biased towards the kidney versus the liver. So that's kind of what's going. That's kind of what we're looking at. So let's see. So we have this data out. I think I can start plotting it, I think. Let me first write a file out real quick. So let me have this results. Let me save that real quick. And then I'm going to do one more thing to this results first. And I'm going to order it based off of my adjusted p-value. So I'm just going to make a new variable called res ordered. That's my results. That's ordered by res $p at comma. So whenever I look at this, hopefully I'm going to save this real quick, and head res order. So now it should be adjusted from my p-value of smallest to largest. So now I basically sorted out this file so that my p-values are sorted, or my adjusted p-values are sorted from shortest to largest. So then I should say this. I'm going to write CSV this file. Hopefully this won't complain. I haven't tested this yet. I should actually run that. Let me write that and run that in the terminal. Okay, no complaints, no complaints. Let's see if that file is there. Hold So everything's here. So now I have this in a table that I can work with later. Again, I'm going to play with these files later. But yeah, so I have my expression value, my base meaning log fold, some other standard deviation, another specific statistic related to the test, a p-value, my adjusted p-value, all on a row, and it's easy to look at. It's easy to manipulate. Okay, so let's see, plot MA. So plot MA. So plot MA. What this is going to do, hopefully, is it's going to plot out my log, my fold change expression data, and label dots that are differentially expressed. So let's hopefully let's see how this looks. I kind of forgot how this looks. I think my processors are running a little slower because I'm streaming because this normally wouldn't take that long. I think it's just because I'm streaming and I'm occupying my processors. It's taking a little bit longer than it should, or it normally would. It'll take longer than what it is for you. My computer's complaining a little bit. So this what I'm doing is I am making a plot. I am plotting out. What I'm going to plot out is my x-axis will be my normalized count, my basically my expression data, and then on the y-axis will be my log fold change. And dots, and it's just going to be a dot plot. This plot MA is just going to run a dot plot whenever it finishes. But I think whenever I'm done with this dot plot, that'll be it for the day. Because I think that's going through everything of just doing the analysis, not looking at our results. I'll save Friday for visualizing our results. This is our the only visualization that I'll actually do today. The rest of it I'll save for Friday is actually visualizing specifics of our matrix. And so what this plot is, again, this is this is normalized mean count. So this is basically average expression data on the x and log fold change on the y. So any of these red dots is colored in a way so that these red dots have a p-value, adjusted p-value of less than 0.05. The gray dots do not. And so anything above the zero are genes that are expressed biased towards the liver, and anything below that are gene expression, are genes that are biased towards the kidney. And so whenever you do this for the same tissue and just do some kind of a experimental treatment, you won't see this many red dots, right? The only reason there are this many red dots is because we're using different tissues. And of course, again, no shit, they're different. They're different tissues. Of course, they're going to have different genes expressed. But if, say, we have thousands of different genes that are expressed, but say we only have 20, then we can actually look at what those 20 genes are, what kind of pathways they are in, what are their functions, and see if we can find any kind of pattern um, that's going to be linked to our experimental design. So, for example, if we were going back to our fatty acid diet mice, maybe there are genes that are going to be higher expressed in the kidney that are better at processing lipids or something like that, or storing lipids. Who knows? But when we have thousands of different genes, it's kind of hard to actually identify and figure out which gene is doing what. However, we can say like so ATP1B1 is biased towards um, is biased towards the kidney. And I promise you, if you look for that gene on ensemble, it will be you'll see kidney expression, right? It is kind of neat. And I forget. I looked at what this gene actually does, but I kind of forgot what it does. Um, But yeah, so this one's biased towards the kidney, that one's biased towards the liver, that's biased towards the liver, biased towards the kidney, etc. So you're going to definitely see the bigger log 2 fold changes. You're going to see a lower p-value. You will see that kind of relationship. And sorry, the last thing I'll do is running a summary of my DDSDE. And so my summary wrong summary, wrong command. Whoopsies. 2 seconds. 2 seconds. Almost there. Almost there. Promise I'm almost there. Summary results. That's the problem. I'll do summary results. Summary res. And so when I summarize my res, right? So this is containing all the results of my DDS experiment, my differential experiment. It's going to tell me that things that are upregulated. So I have 4,000 genes that are upregulated. That means that they're biased towards the kidney, or sorry, biased towards the liver, and 4,000 genes that are biased towards the kidney. Right? Again, thousands of different genes. It's like 8,000 genes overall that are differentially expressed in one form or fashion. But yeah, I'll call it here and probably spend another hour or so on Friday describing ways that we can visualize our data. Yeah, that's it for today. Finally.